Hi everyone, this is Professor H. Rahman from Agricultural and Food Engineering Department, IIT Kharagpur. I welcome you to this NPTEL course on traction engineering. This is lecture 18, where I will try to cover tractive performance prediction models. Basically, what is developed by Wismer and Luth. The concept which will be covered is wheel numeric, motion resistance ratio, torque ratio, and effects of tire cell variables on tractive performance. So we have basically derived the theoretical equations which will be necessary for developing the tractive effort. But if you look at those equations require what is the distribution of normal pressure, what is the shear stress distribution. So in practical field, it becomes really difficult to do that exercise. So what you have to do is some equations should be available, so that easily, if you know this is the weight which is coming and this is the soil condition, then immediately you can say, okay, this is the available pull, or this is the available or this is the rolling resistance. So to do that, there are scientists. They have carried out this kind of activities, and based on different field data related to tractors, soil, tire combinations of different sizes, different soils. Then, based on the single wheel testing data, scientist Wismer and Luth he has developed some equations related to tractive performance evaluation. So basically what he has done is he tried to identify which are the parameters which is going to affect the performance parameters. Performance parameters means your pull, rolling resistance, tractive efficiency, etc. So he tried to identify this in terms of soil parameters, in terms of wheel parameters, in terms of system parameters. So let us see what are those parameters. Under soil, he identified a parameter called cone index. Basically, cone index gives the force required to push a concept probe into the soil. That means it will give indirectly the strength of soil. So it is symbolized as Ci, and its dimension is Fl minus 2, force per unit area. Next, he identified what are the wheel parameters. Under wheel parameters, Wismer and Luth, they selected tractor section width, overall tire diameter, and tire rolling radius. And these are denoted as B, D, and R, and the units are length units. Then he tried to identify what are the system parameters. Under system parameters, he identified these are the parameters like load. How much is the load acting on the wheel? What is the force required to tow the wheel, which is nothing but your rolling resistance? Then what is the pull which is developed? Then what is the gross tractive force, which is basically the summation of pull and rolling resistance. And while developing the gross tractive force, what is the corresponding slip? So he has identified 9 parameters, and he applied dimensional analysis technique to find out the relations, the dimensional ratio variables to develop that equation. So if you are applying Buckingham's pi theorem for dimensional analysis technique, then 9 minus 2 will be 7 dimensionless variables. So what are those 7 dimensionless variables? One is your towing force upon W, pull upon W, tractive force upon W. So I have indicated here rho as towing force upon W, mu coefficient of traction, which is nothing but P upon W, and mu G is the ratio of thrust upon W, tractive force upon W. They are the functions of cone index, they are the function of the tire parameters, they are the function of wheel slip. Now, these parameters he tried to combine to find out 4 different dimensionless ratios. So, what are those parameters? One is CIBD by W. That means he has combined the strength of soil with size of the tire B and D, and then W, what is the weight coming on the wheel. So, CIBD by W, that is called as wheel numeric. He has combined these parameters of soil, parameters of wheel, and what is the external load which is acting. So, this is denoted as wheel numeric. Okay. Then he defined another parameter, dimensionless parameter B by D, then R by D ratio, then S. Slip is dimensionless, so R by D, B by D. So, using these 4 parameters, he tried to find out relationship, and he developed 2 equations, one for pull, the other one is for rolling resistance. If you look at this one, CIBD, there I have indicated that tire rolling radius R by D. R by D for most of the tires is around 0.475. That means it is basically a constant factor. It is not varying for the agricultural tires. The other parameters which are varying is B by D and the slip. Slip again depends on what is the type of soil and what pool is developed. So, that depends on, slip is dependent on that. The only thing which is left is B by D ratio. So, Wismer and Luth, they said they have taken B by D ratio as 0.3. For all combination of tires, they have tried in different soils, they have maintained that B by D ratio as 0.3. And for all agricultural tires, they have taken del by H ratio, that means tire deflection to section height ratio as 0.2. So, these are the practical limitations, in the sense under these variables he tried to develop some equations. Let us see what are those equations which are developed by Wismer and Luth, and then we will discuss what are its limitations later on. Now, he has developed this equation, motion resistance ratio, which is nothing but the ratio of towing force to weight coming on the wheel. Weight, when I said this is a dynamic weight. In case of a tractor, when it will try to pull an implement, there will be weight transfer from the implement side as well as from the front axle. So, the weight transfer is there. So, that means if the static condition weight distribution is 70-30 or 65-35 in the rear and the front axle, then the 65% will be increased. Okay. So, if you take only 65%, that means there are 2 wheels on the rear axle. So, 65% of the total weight divided by 2, that will give you the weight coming on each wheel. Now, during pulling certain implements, since there is some weight transfer, so what will happen? This 65% divided by 2 has to be increased. So, we should know what is the dynamic weight which is coming on the wheel. Then only we can find out what is the motion resistance ratio. So, the W which I have indicated, I have written as dynamic wheel load. Okay. Now, this is equal to 1.2 divided by Cn. Cn is your wheel numeric plus 0.04. Okay. So, Cn is CIBD by W, and Ci is to be measured following the procedure which is given in American Society of Agricultural Biological Engineers standard 313.2, and we have to measure the tire section width, we have to measure the overall diameter. So, then only you can find out the value of motion resistance ratio. So, when I try to plot it versus different wheel numerics, so the wheel numerics are varied from say 5 to 70, then the nature of the curve will be like this. Initially it was very high, then afterwards it drops very rapidly, then it becomes almost constant after 35. Why it is so? And what does it reflect? When I said wheel numeric is 5, wheel numeric is 5 means CIBD. For a given tire size of the pneumatic wheel, BD cannot be changed. Only change is your CI, that means strength of soil. So, when the soil is soft, what happens? Strength of soil is less, so the wheel will try to sink. Okay, so resistance will increase. So, CIBD by W will reduce because CI is less in soft soil, so CI will reduce. So, it will move to, if you are taking the center point here, then it will move towards this one as the strength of soil is reduced. If the strength of soil is increased, it will move towards this right side. So, strength of soil is reflected by cone index. So, that means if soft soil, we will get more rolling resistance. If hard soil, then will move toward the right side, we will get the lesser rolling resistance because sinkage is less, compaction is less, so rolling resistance is less. So, basically on hard soil, it is the tire deflection. Okay. So, that will give rise to rolling resistance. But if in case of soft soil, it is not the tire deflection, it is the sinkage that will come into picture. So, the nature of the curve is well justified looking at the strength of the soil. But the only difficulty is it does not differentiate between a powered wheel and a rigid wheel or a towed wheel. It will give the same value. If it is a powered wheel, if it is a unpowered wheel or towed wheel, for both the cases it will give you same value of rolling resistance, which is very difficult to say. Why? Because when there is a slip, certain amount of sinkage will be there, so that part is not reflected. So, we will discuss in detail what is the other difficulties. Let us now move to the other equations which has been developed. The second equation which he developed is related to gross traction ratio. So, gross traction ratio means it is the ratio of the tractive force which is developed at the contact patch divided by the dynamic weight coming on the wheel. So, in other words, we can replace F with Q by R. So, Q by R, Q is the torque which is acting on the axle and R is the rolling radius. So, that way thrust into radius will give you Q. So, we have replaced F, that is tractive force, with F into R, tractive force into rolling radius as Q, and F we have replaced as Q upon R. This rolling radius is found out on a hard surface, hard smooth surface at self-propelled condition. Okay, we have to run the wheel and then taking the number of revolutions, we have to divide it by n into 2 pi. Suppose we make 4 revolutions, then whatever distance it covers, d divided by 4 into 2 pi. So, that will give you what is the rolling radius. Okay. Now, Q upon RW, and W is the dynamic weight, that is equal to 0.75 into 1 minus e to the power minus 0.3 CNS, where Cn is the wheel numeric, S is the slip. So, once you know the gross traction ratio, if you deduct the rolling resistance ratio, then it becomes F my W minus R rolling resistance by W. So, that will give you pull by W. That means this is your coefficient of traction. This is your motion resistance ratio, MR, and this is mu G. Mu is coefficient of traction and rho is the rolling resistance. So, when I deduct it, then it becomes, this is the equation for the pool which is developed, pool by W ratio, 0.75 into 1 minus e to the power 0.3 CNS. This is gross tractive effort into minus 1.2 by Cn plus 0.04. So, that will give you the coefficient of traction, and slip we define as 1 minus BA upon BT. BA is your actual speed and BT is the theoretical speed. Now, when you try to plot this P by W, that means net traction ratio versus wheel slip starting from say 0.01 to 100%. So, and this has been plotted for different soil conditions which are reflected as wheel numeric at 10, 20, 30, 50 like that. So, what we observed is when we decrease the slip, the nature of the curve, what we say, we are getting lesser slip. Whether it is at wheel numeric 10 or whether it is at wheel numeric 20 or whether it is at wheel numeric 30, if I draw a line somewhere at 10%. So, this is the pool which is developed, COT. Now, when I increase the pool to the slip to 20%, then you can see this is the case. So, that means after certain slip, these values are almost maintaining a constant value. Okay. But in case of this wheel numeric, when it is 10, it is still increasing beyond say 80%, you can say, it is still increasing. So, what does it 10 indicates? That means the soil is soft, CI 10, and CI 50 means soil is hard. So, in hard soil, the pool which is developed or the COT which is developed is much higher than the COT which is developed in soft soil. That means, if you look at this point, there is a difference of nearly 0.45, 0.5 like that. Now, at 20% slip, again same difference. If you look at this one, so there is a difference of 0.45. So, we conclude from here that the P by W or the coefficient of traction is more in hard soil. That means, in hard soil, the tractor could be able to develop more pull. In soft soil, the tractor will be developing less pull. Why? Because the power is lost in overcoming the rolling resistance. So, the net pull available will be less in soft soil. Whereas in hard soil, the rolling resistance is lesser, hence your pull developed will be more and your coefficient of traction will be more. Now, once we know the coefficient of traction, then rolling resistance and gross coefficient of traction, then the one most important component which is computed while calculating or while evaluating the performance of a tire is your tractive efficiency. So, tractive efficiency is basically the output by input. So, in case of a tractor or in case of a single wheel, output is your drawbar power or output is your tractive power, okay, and which is the pull into forward speed, and the input will be your axle power. So, if I take the ratio, so tractive efficiency will be equal to mu upon mu g, so into 1 minus s. So, P by W, which is the coefficient of traction, and the denominator is Q upon RW. Q by R is the tractive force divided by W into 1 minus s. So, this is basically derived from fundamental equations. So, once you know those equations which have been developed by Wismer and Luth, next is we can put those values here to find out the tractive efficiency. Now, based on the output data from Wismer and Luth, it has been plotted how the pool to weight ratio is varying. That means COT is varying, which is indicated by these blue lines, and the tractive efficiency is varying, which is indicated by the dotted green lines for different fuel numerics, CIBD by W, starting from say 10 to 50. So what we observed here is the sleep at which you are getting maximum pool or COT value and the sleep at which you are getting maximum tractive efficiency. If I draw a line, suppose at fuel numeric of 50, this is the maximum tractive efficiency we are getting. So this corresponds to a wheel slip of say around 8%. Now the maximum pool which you are getting is from this point only, 30%. So there is a difference. The sleep at which you are getting tractive efficiency, maximum tractive efficiency, the sleep at which you are getting maximum pool. Now if you look at 20, suppose this is 20 line. So maximum we are getting maximum tractive efficiency is here, which is corresponding to say sleep of say around 15%, and the pool which you are getting at 20 is still increasing, so maybe around this. So sleep is here. We need more power to be developed, at the same time we need more efficiency. So what to do now? We have to compromise between whether we require more pool or whether we require more tractive efficiency. Okay, so that's why a design tractive efficiency curve is given. So it is and at the higher wheel numeric values, it is the corresponding slip is 15%. At lower wheel numeric values, the slip is more than 25%. So you have to find out a suitable slip value to make a compromise between this design, between the tractive efficiency and the COT. But nevertheless, the equations which are developed by Wismer and Luth are very simple in the sense only 2-3 parameters are required to compute the performance parameters of a wheel. The limitations, if you look at, maximum tractive efficiency reaches a maximum at a relatively low slip value, and then it decreases with increase in slip. Okay, so maximum tractive efficiency occurs at lower slip values for the larger CN values, which are associated with higher soil strengths. That means when CI is more, cone index is more, you will get better tractive efficiency. Or wheel loading is less, then you will get better tractive efficiency. To get maximum drawbar power output, the vehicle or the wheel should be loaded to cause slip which is occurring at maximum tractive efficiency. Okay, otherwise you will not get maximum output. So we have to load the wheel in such a way that the slip should be around this. Suppose in 50, so we have to load in such a way that the slip is around 5% and get the maximum tractive efficiency. And if you require more pull, then you have to have more slip. Then only you get maximum pull. So that's why in the end I have a P by W ratio, that is COT ratio. Coefficient of traction is not close to its maximum value at this slip. If this is the maximum tractive efficiency, the slip corresponding to maximum tractive efficiency, at here only you are getting 0.3, whereas at 30% you are getting near to 0.72. So you have to make a compromise between maximum COT and maximum tractive efficiency. Now looking at the limitations of Wismer and Luth's equation, The motion resistance ratio, as I told in the beginning, it doesn't contain a slip turn. So that's why it will predict the same value of motion resistance for a towed wheel as well as a powered wheel. Applicability of equation which is developed by Wismer and Luth is only limited to B by D ratio as 0.3, del by H ratio as 0.2 and R by D ratio as 0.475. So these are the limited applicability. If you exceed B by D ratio, if you exceed del by H ratio, or if you because R by D ratio is nearly constant. So these are the two values 0.3 and 0.2. If you exceed, then applicability of Wismer and Luth is not known. And the another limitation is, if you look at the equation given by Wismer and Luth, maximum you can develop 75% of the torque which is applied to useful to tractive force. That is another limitations. So with these limitations, since these equations are very simple and they can be easily handled, so that's why it was getting popularity earlier. So I took these equations and tried to discuss. Thank you.